talks to animals. Hey, I'm Mark Wahlberg. You guys know me. Let's go talk to some animals. Hey, dog, how's it going? I like your fur. That looks really great. So you're a dog, right? What's that all about? Okay, well, it was great to meet you. Say hi to your mother for me, okay? Now I'm gonna talk to a donkey. Hey, donkey, what's going on? You're a donkey. I like that. You eat apples, right? I produce entourage. Okay. Talk to you later, donkey. Now I'm gonna talk to a chicken. Hey, chicken, how's it hanging? A lot of people want to eat you, but I just want to talk to you, okay? We should do a film together. What do you think? Chicken, I'm not joking around, okay? This is the real thing. I mean, this could be huge. All right, well, think about it. Say hi to your mother for me, all right? Now I'm going to talk to a goat. Hey, goat. It's good to see you. I like your beard. I had a beard like that in The Perfect Storm. Did you see that movie? Did you see The Perfect Storm go? Say hi to your mother for me, okay?
This has been Mark Wahlberg Talks to Animals.
Welcome to Computer Science 50. This is the end of week 5, and I have absolutely no connection to the course for that clip. I was looking at Tina Fey, Sarah Palin videos last night, and somehow came across that one. And thought rather than take a political angle here in 50, we'd play that one instead. A couple of announcements. So Quiz 0 is coming up next Wednesday, recall. The only handout for today is this little informative sheet that tells you pretty much everything you need to know. Note that it mentions we will not be here next Wednesday. Instead, there's 3 different locations where you'll actually have a place to write with paper pencil. Take a look at where your last name tells you to go that day. We will be in here, same time, same place on Monday for lecture as usual. And note that we have a couple of reviews coming up. So this Friday, during what would be lecture time, 1 to 2:30, the teaching fellows will be holding a review session in Northwest Science, B101, which is a really nice new building just down Oxford Street, roughly across from the Computer Science building on the right near University Museums, down in the basement level. So do check that out if you would like to partake in the course-wide review. It will be filmed and placed online by Sunday if you can't tune in person. And the teaching fellows on this Sunday, Monday, Tuesday will also be holding in-section reviews for the quiz as well. So you should have plenty of prep underneath your belt, and this sheet should give you everything else that you need to know. David is going to eat lunch alone this Friday so that he doesn't send mixed messages as to what you should be going to at 1 p.m. on Fridays. So the review will supplant the regularly scheduled lunches. Besides that, no lunch review. Any questions whatsoever? What do you got? Anything? No? All right, so let's pick up where we left off and then take a look not only at Sudoku, but also some of the security threats that I've been hinting that are possible with all the stuff we've been talking about. But rather than focus on Sudoku itself, what I thought I'd do, just to give you a sense of one of the goals of this problem set, is to show you a little sample program that I whipped up here. So literally just before class in the hallway, I decided to be neat, or at least illustrative, to show a demo of ncurses. So ncurses is this library, ncurses, that you're going to be using for this problem set. And it's our attempt to introduce you to a full-fledged third-party API, application programming interface. And this is a fancy way of describing a whole bunch of code that other people have written that you yourself might want to integrate into your programs so that you don't have to go reinvent some wheel, namely the ability to have a graphical user interface. So curses, or ncurses, is what's going to give us our little menu bars, it's going to give us our colors, and it's going to give us the ability to move the cursor up, down, left, right, which we really haven't been able to do using things like printf and getString and the like. So this is all it takes to write a curses program. The very first thing at the top of the file is just include ncurses.h. I've not bothered commenting this because I literally wrote this on the heater in the hallway out there. But I wrote my main routine here, and then I looked, but just by looking at the manual, the documentation for ncurses, as to how to start an ncurses program. Turns out the very first thing you need to run is a function called initScr, or initScreen. And this is just a function that comes with this API, with this library, that starts everything up and configures your terminal in a way that will support this ncurses library. This next function does what the name says. It starts color, so that if the user actually has a color display, which these days is pretty typical, though back in the day we really were talking monochrome displays for the most part, this kickstarts the process of enabling color in the user's display. To be sure, you have to have certain settings right. Some of you have stumbled across this and have chatted on the bulletin board about it, but look to the the problem set's footnote that discusses how to enable color in, say, secure CRT if need be. This third line, and this last one related to color, goes about initializing color, a specific pair of colors for the program. So the way ncurses works, because you still have a fairly primitive interface, is it allows you to assign a foreground color and a background color for every character on the screen. And a typical terminal window is, what do we keep preaching? What width by what height? So 80 by 24, though just by double clicking the window can you usually expand it to something bigger than that. But 80 by 24 historically was the default. And so what that means is you have 80 characters laterally and 24 characters up down. So that gives you a grid of characters. And every one of those characters can take on a foreground color and a background color. And the way you associate foregrounds with backgrounds is that you choose an somewhat arbitrary number, like this is my first color pair, and my foreground color is going to be this constant called color black, and my background color is going to be this color called color red. And the means by which I knew this is if I pulled up the man page for, say, init color and scroll down, you would see in the man page the relatively limited number of colors that ncurses supports out of the box. But if you actually want to tinker with RGB values like you would in Photoshop, can you actually get other colors as well? But we'll just use the basics. So this is a pair of colors for black foreground text and red background. Well, the next thing I decided to do was I'm going to declare a variable y and x, and then I'm going to call this macro. So this is not a function. This is actually a macro whose distinction doesn't really matter for this afternoon's purposes. But what I'm doing is passing it 3 arguments. One, this constant value, essentially, called standard screen. So curses provides you with the ability to break your screen up into multiple smaller screens, these rectangular regions. For simplicity, problem set 4 just gives you one big screen, one window that fills the whole window. We kept it simple. But this macro requires that you specify which of those rectangles you care about. So I just hard-coded in the standard screen. And then I passed in y and x. And the only thing that's a bit annoying about this macro is that almost any other time when we've told you to pass in arguments that are designed to be changed, have values inserted into them, we would have to prefix y and x with what? So an ampersand. But because this is a macro, which is this clever trick that the problem set talks about, you actually can pass them as though it looks like pass by value, when really underneath the hood it is in fact being passed by pointer or by reference. So, that's the illusion it's trying to create. So now I just have this Boolean variable, whose role will become clear in a second. And then all I wanted to do was iterate from left to right, top to bottom, over every one of the 80 by 24 characters on the screen. And just to demonstrate how you can use the simplest of curses features, I just wanted to plop a char down in every one of those squares, every one of those characters. And the character I wanted to lay down is quite simply the white space character. I literally hit the space bar, put it between single quotes, and that's it. So why is this going to be at all interesting? Well, I've done a slight bit of fanciness when it comes to this Boolean variable. I said in this iteration of the loop, if that Boolean variable called on is true, we'll go ahead and turn this thing off. So this is another ncurses function, attribute off, that's turning off color pair number 1. But if by contrast this variable called on is false, what that implies to me is I want to turn on the attribute called color pair 1. So the idea is I'm going to turn color on, off, because by default the colors on the screen are just black and white, not black and red. And then this is a little trick that results from our using the bang operator. So what does this line of code at the very bottom, on gets bang on, do effectively? Yeah, it flips the value of this Boolean variable. And to be sure, we could have done this in a couple different ways, right? I could have been more explicit and added some curly braces here and said, well, in this case, if on is true, well, now on should get false. And then down here, I could actually have the opposite of that and say on should get true. But why bother if you can sort of simplify it into something that's still just as straightforward? So that's it. So actually, not quite it. So there is one more line of magic. So with ncurses, for efficiency reasons historically, the goal is to update individual characters on the screen, unlike printf, which has you dump a whole bunch at once wherever the cursor is. I've gone ahead now with this loop and touched every one of the characters on the screen. But for efficiency, my terminal is not going to display any of those changes until you explicitly call this function called refresh. And this is so that all of the changes that you've kind of queued up in memory are finally dumped to the screen when this refresh function is called. Now, this is an intentional infinite loop. And notice I didn't even bother closing out curses nicely. At the end, you're supposed to call endWin and do a couple of other things. But clearly, if I have a while1 loop at the very bottom with nothing more than a semicolon, that's just going to be a perfectly infinite loop. Well, the only reason I wanted to do that was I wanted all of my colorful changes for this demo to stay on the screen before the program just quits out and undoes everything we just did. So I'm going to go ahead and run make on this. So make ncurses. But I'm going to run into a whole lot of problems. And why is this? There's a pattern here, though. Undefined reference, undefined reference, undefined reference. When you've seen that in the past, you've probably left off what? Yeah, so the library, the linker flag. So -L CS50 is a common mistake that folks have tripped over. -LM for the math library. And in this case, -L ncurses. So rather than use make, since I don't even have a make file to simplify this, I'm actually going to do it explicitly. So gcc ncurses -.c -o, make the program called ncurses, but then link in the ncurses library. That made it happy. So now I'm going to go ahead and run the ncurses program. And what I get is something that's a little ugly, but it does show this sort of cyclical pattern of being on and being off. And actually, this is wrapping a little weirdly. If I actually had done this with a smaller font, it would look more like a checkered pattern. But the point is just to turn these colors on and off. All right, so that's it. So when it comes time to problem set 4, when you're implementing this, that's sort of all it amounts to. You now have the ability, much like a canvas, to sort of paint characters anywhere you might like onto the screen. So if you haven't yet dived into problem set 4, do take a look at this past Monday's wonderful walkthrough led by a substitute Cato this week. All right, so with that said, we left off here. So CS50's library, we started to peel back the layers of it. And we looked at getInt and getChar, and they were pretty much identical. And the secret sauce to those functions was this use of scanf or scanf. And that allowed us to not only read in a character from what's otherwise a string and convert it automatically to like an int or a float, but it also allowed us to do some error checking. And it did that using that format string with like the trailing %c, like we said on Monday, so that you could detect some superfluous character or characters that you just want to give up on if the user has provided too much. But let's try to home in now on exactly what that technique was. So what you'll find in this code was included last week, so there's no additional handout still. In scanf1.c, we have this very simple program. And the comment at the top of this file says what it does, but let's just focus on the code for a moment. So I seem to be declaring an int called x. I'm just asking the user for a number, please. And then I'm using this scanf function. So scanf %d, comma, ampersand x. And to be clear, why do I need to pass in x as ampersand x and not just x itself? Yeah. Yeah, so you want to actually put a value into x instead of getting one from it. So by passing an ampersand x, you're passing not x itself or a copy of x's 32 bits, but rather the address, the 32-bit address of x, so that this scanf function, whoever implemented, can literally go follow, or can figuratively go follow that arrow somewhere in memory, find those 32 bits, replace them with whatever the user has typed in after this string, number please, and then it can load it into that value x. So this isn't a very fancy program, so let's go ahead and just make it to see what it does. All right, it seems to have compiled. Let's run scanf1. Number, please. Give me a number. I heard 46, the loudest over here, and in fact 46 was correct. All right, so the program works. Not all that interesting, but now let's do something dangerous with the same function. So you'll find in scanf2 very similar construct, but this time I'm using a string or a char star, a buffer of chars, because now I care about reading in not just a number, but a string from the user. And I claim atop this file that this is, in fact, a possible attack vector this program has. Why is this program buggy? almost identical to the last one. Yeah? So there's no size checking specifically in what sense? In what context here? Yes, so this program seems to read in an arbitrary number of an arbitrary number of characters, and in fact, where does it plop those characters once read? Well, scanf, just like printf, can be passed things like an int or a float or a string, aka char star. So the idea of scanf here, in passing it this buffer variable, is effectively to say plop whatever string you've read in into the buffer called, in this case, buffer. And a buffer in this case is presumably supposed to be an array of characters, a sequence of chars next to each other so that there's room to drop this string. But push harder on this. Like we're certainly not checking length, but what else have we completely failed to do here? What's that? Yeah, so we're not checking the memory certainly, but what have we asked the operating system for? In writing this line of code, char star buffer, literally, what have we asked the operating system to provide us with? Someone's got to speak a little louder. A string of indeterminate length, and even more precisely, an address of a contiguous block of characters. We've only asked for 32 bits, and those 32 bits, by design of this data type, char star, are really meant to store not even a char, but rather the address of some char, or implicitly an address of a whole bunch of contiguous chars. So where are we about to read this string into then, when scanf is past buffer? Well, let's take a quick look. So I'm going to go ahead and make this with just make scanf2. OK, it's already built still, so let's go ahead and run GDB on it. So GDB scanf2. All right, so this is, again, a useful tool. And if you have yet to whip out GDB during a problem set, do start. It will become an increasingly powerful and useful tool, although with the current problem set 4, it is a bit tricky to use it as effectively because you have these graphics getting in the way. So if you're going to sort of stall one more week, that's sort of acceptable, but certainly with problem set 5, will you find this a useful tool? So how do I pause this program when we hit main? All right, yeah, so break on the function called main, or I could write in the actual line number, 19. Now I'm going to go ahead and type run to run my program. I've paused before this line of code is even executed. I'm going to type next to go ahead and let that execute. And it didn't print, though. We've seen this before. Why did nothing actually print? It's like the third time I've asked this question. Why did nothing print, even though printf was just called? Exactly. It's in the standard output buffer, right? So because there's no \n, there's no \r, there's not even a whole lot of text there, for performance reasons, the program has just decided, you know what, those characters will get printed, but not yet, because I see no reason to just yet. So had we put a \n, they would have appeared, and if we keep running the program, they will eventually appear. But let's now focus on this scanf line. So if I type list, I'll see my code for sort of a quick reminder of what's there. So I'm actually curious to see what's currently inside buffer. And buffer is just a variable. It's a variable of type pointer, a pointer to a char. So what I should see there under normal circumstances is some kind of address. And the scheme that a computer, at least C and GDB, use to describe addresses generally is not a big decimal number, but a hexadecimal number, which uses 0 through 9 and A through F. And it's just because you can represent big numbers more compactly with fewer digits. But let's go ahead and print buffer. And in fact, we see the address. So this cryptic looking thing here is 0x, which just means here comes hexadecimal, B7F25DC0, which generally is meaningless, but at least in this context hints at what is inside of buffer at the moment. Well, what GDB does for us too is because it knows, oh, this variable is of type char star, that generally means you care about a string. I'm going to go ahead and go to that address for you, and just for debugging purposes show you, even without being asked, what is at that address. So if I wanted to be more specific and say go to the address in buffer, well, remember that the syntax for that is star buffer. So that's the dereference operator. Take the address and go there. So if I print that, what I should see is, yep, the first letter of what was predicted to be there. Because it's just a pointer to a char, so you print out star buffer, and you're going to see what's at that specific address, which is u. Now, does this u / whatever have any interesting meaning? No. I mean, it just means that there's some garbage there that we shouldn't really need to worry about. But here's the problem. When we now call scanf and read in a string, we're telling scanf to put the string that the user types at what address? 0xv7f25dc0. And now that doesn't seem so problematic because, frankly, who really cares if we overwrite whatever this garbage is? But that's kind of a dangerous assumption, right? What if that actually is just the ASCII manifestation of some bits that are actually important, an integer that's important, a float that's important, right? Even though it's being displayed as garbage, it's still bits, and they might very well be useful bits, and they might not even belong to this function, but maybe some other function that's been called or something that's on the heap. So if I go ahead now and read in some string into buffer, it's going to plot them at that memory address, so it will overwrite the u. And if I've typed in multiple characters, they'll continue to overwrite that garbage there, but just without any checking of the length. And in fact, do I own any of that memory in the first place? The only thing you own is the 32 bits in which this address itself is being stored. You don't actually own anything that is referred to by that address yet. So the result of this, if I actually try to bang on this program and provide it with some big inputs, is going to be what? Probably a seg fault. Yeah, even with one character, what's just happened is I've tried to read into a valid address, but that points to memory I don't own because I haven't allocated it explicitly yet, some character like A. And the operating system doesn't like that because, again, I'm trying to touch memory that is not mine. Just to be clear, let me go ahead and run one other trick. So GDB of scanf2, and then I'm going to put a space and write core. Because if you do an ls, you'll see that core was this big, relatively big file that was dumped out. It looks like it's 172 bytes at the moment. When you're in cloud.cs50.net, you'll notice that the naming scheme for these core dumps is actually core dot and then some number, so that you can actually have multiple core dumps in the same directory. So just realize that slight difference. At the moment, I'm on nice. So I'm going to run GDB of scanf2 core. So we've not yet typed in core, so this isn't meant to be argv. Notice that some more stuff happens. It's like loading symbols. So it's apparently using that the bits inside the core to be slightly more helpful to me. So notice at the very bottom here, it says core was generated by scanf2. All right, so that I knew already. Program terminated with signal 11 segmentation fault. Don't really know what signal 11 is, but at least I'm familiar with segmentation fault. Probably means some kind of memory. And this is kind of interesting. Number 0, this is referring to the stack frame in question. At that address, in apparently some function called iovfscanf from who knows who wrote that. So that's in the standard C library, libc. Anytime you see something like that, you can kind of infer it's someone else's code that comes with the system or comes with the compiler. So just based on the name, who do you think probably invokes this function called iovfscanf? Probably scanf. So whoever implemented scanf probably wrote scanf in such a way that it calls some other function, and as soon as that function got called and that function actually tried to touch the memory that you don't own, it's what caused the program to choke. So there's some kind of sequence of events. And if I go ahead and run backtrace, which is another useful GDB command, which I've not shown in lecture just yet, backtrace is wonderfully useful because you have no idea, presumably, where to even start in debugging a function called vfscanf. Because in fact, that's not even your function. It's someone else's, so it's not even your concern, assuming that person implemented it correctly. But what these numbers now show when I've run backtrace is that, yeah, the most recent stack frame, number 0, is the stack frame that belongs to some function called vfscanf. But the guy who called that is actually something called scanf, or just to be really precise, that function really is called ISO C99_scanf. That's how it was implemented. But more interesting than that is that the guy who called that function was apparently main, and that does belong to me. And specifically, it was called at line 20. So by looking at the stack frames, and this is, again, sort of GDB's depiction of this picture, so going sort of back in time and numbering those stack frames, can I then realize, oh, scanf2.c, line 20. Let me go ahead and open that. So scanf2.c, let's go to line 20. Aha, so that's the line in question. Now this is such a simple little program, it didn't take a huge leap to figure out where the bug was. But with a larger program, when you're trying to figure out why in the world your program seg-faulted, henceforth absolutely run gdb, your program's name, followed by the name of the core file, like core.123.4 if you're in the cloud. Run that, then look at where the error message is saying something happened, type backtrace, and you'll see sort of a moment in time, a snapshot in time of what was happening and what was where in memory when your program crashed. And it's so neat, GDB, that you can actually jump around those stack frames and actually look at variables. So just to show one other trick, if I run backtrace, each of these frames again has a number. If I want to, even though I'm technically in VF-scanf now, so to speak, I can type frame and then the number of the frame I want to move to while this program is sort of paused in time. Now I'm in mains frame. I can type list and see my code there. And even though the program is currently running and has crashed on VF-scanf, I can actually say, you know what, I'm kind of curious to see what was in buffer at this point in time. So using GDB, even if you have a stack frame here for main, another one here for scanf, another one here for VF-scanf, you can literally take a look at any one of these frames just by using the backtrace and the frame command. And you can sort of pop around. And this is why debuggers are so powerful. You don't have to just print out variables with printf ad nauseum. You can instead pause your program or accept the fact that it crashed and then poke around, sort of like a diagnostic technique, an autopsy, so to speak, for a computer program. So there's some neat stuff you can do. But we began this story by claiming that this is bad. And this is bad because what are we allocating for buffer? A 32-bit pointer, and that's it. So let's do one step better. How do we fix this particular bug? What do we replace this declaration with? Let's assume the user is really not going to type anything more than a first name. So that's the context here. Well, first name, even being generous, is probably fewer than 32 characters. If I want to be really paranoid but a little wasteful, 1024 characters. Maybe I can even go up from there. But, you know, somewhere you have to draw the line. So in fact, in scanf3.c, we draw precisely that line. So in this third version of the program, I still declare a buffer, but this time I sort of simultaneously reserve the memory for those characters. Size 16. So it's a little different approach. We're using an explicit array instead of using a pointer and then that trick called malloc that we saw on Monday. But this program looks like it might work. If my buffer's of size 16, let me go ahead and compile scanf3. Go ahead and run scanf3 and then try some things. Foo. Thanks for the foo. All right, so foo, foo. Okay, how about foo, 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 foo. At some point, what should happen? Okay, so it thanked us and then it freaked out because it was not within the limits of the string. So this kind of suggests that as simple as some of these functions are, scanf and declaring arrays, you can really easily do some damage. In fact, there's no obvious way in this program to check how many characters the user has typed in. Right, so how did we deal with this with the CS50 library? Well, notice that for the CS50 library, CS50.c, when we implemented the getInt function, yeah, we did in fact use scanf, scanf, to scan a string, not whatever the user typed at that moment in time. But because we used %d to grab the user's input, we're sort of implicitly bounding how many bits we're going to suck into memory. Because a %d implies an int, and an int is only how many bits? 32. And in fact, even though we then said %c is generally, well, it's a character, which is only how many bits? 8. So maximally, this little line of code is only going to suck into memory, into RAM, 32 plus 8, so 40 bits total. Even if the user typed more, those additional characters are going to stay in the standard input buffer. They're going to sort of linger until we deal with them. But here, we're sort of implicitly bounding how many characters we're reading in. But how did we actually implement getString? Well, we won't dwell on all of the details because we did do that Monday. But notice that when we grabbed characters from the user, what function did we use for getString and getString alone? The hint is highlighted in green. Right? We used fgetc, which meant file get character. So fgetc. So we literally got the user's input character by character. So conceptually taking baby steps across the user's input, because what did we have to do after reading each character before we proceeded to get the next one? We had to check if we had enough room, right? We had to check if we had exhausted the capacity of the buffer, because if we had, we then need to allocate a new buffer, potentially copy over all the original characters into the new buffer, and then get rid of the original buffer. And we did that with that function called realloc. And then later in the program, remember, or later in the function then, we created a new array that's a new buffer that's of precisely the right size, copied all the chars into it, and then got rid of the excessively large one. But this is really a pain in the neck, right? This is why you use libraries written by other people, because it's kind of a pain if just to get users' input safely without risk of crashes and seg faults and today security threats, you have to read the damn input one character at a time. And this is why there's this theme in programming and computer science of building layers and layers on top of previously done work so that you yourself don't have to worry about some of those underlying lower level details. But the upside, or the implication of all this, is that you can do some pretty scary things. So I didn't bother printing out a couple slides that I inserted for this week. They are online, but there's not too much on them. So this is my claim of several dangerous functions. So it turns out there is a function that years ago was very commonly used called getS, and it means get string. How does it work? Well, I'm going to go ahead and run man getS. It looks like this function here is in a man page that describes a whole bunch of functions together. So let me scroll down to actually the getS one. So getS reads a line from standard in into the buffer pointed to by S until either a terminating new line or EOF, which it replaces with the null character. No check for buffer overrun is performed. See bugs below. So the world finally sort of accepted the fact, or made more clear the fact, that this function is very unsafe. Here's its prototype. So this function getS does return a string, as implied by the char star there, and it takes a string, or rather it takes a pointer to a character, aka a string, as its argument. But notice it does not ask the user, the caller, for what other piece of information that might actually make this safe. How long is the buffer called S in this case, right? Because without that knowledge in advance, getS can just kind of blindly read characters into that buffer called S, but it itself is never going to stop until it actually encounters, per the man page, a \n or an EOF character. So it's entirely up to who to do that sanity check. The caller, you, the programmer who's using this function, but you're in sort of this weird catch-22 whereby you can only get the input from the user by calling getS, but only once you've gotten the input can you check what? How much there was of it, right? So you can kind of cheat and say, please do not type more than 16 characters at the following prompt. But that's not exactly the safest approach to take. But fortunately, there are better functions. So there's fscanf, which is file scanf, which is more of a generalized version where you can read characters from a file or from these streams called standard in, for instance. But there is also this function we've seen already called scanf, but there is a safer version of it called fscanf. And if we look at those same man pages, let's go ahead and look at scanf's man page. It too is clumped together with a bunch of related functions. And in fact, here's mention of those VS functions we saw a moment ago. So they are in fact related. So fscanf appears to do this. It doesn't even return a string. It returns an int, which is kind of interesting. It takes a file star pointer as its first input. And we will see those today. But then it takes as its second input a format string, the quote-unquote printf-like thing, and then followed by a whole bunch of variables, right? The substitute variables like &d and &c, like we've seen in some of those examples. So the way this actually works then is that you pass it in something similar in spirit to what we did in scanf3, scanf3.c, but instead of just passing in, let's do man fscanf here, fscanf, oh, that's not actually fnscan. I just lied. Okay. David will fix this later. Okay, what I just said to you, this does not actually solve that problem, because nor does fscanf actually check the length, because among the arguments I just rattled off, nowhere mentioned was some mention of size. So let me go back and I will fix that a little later. But let me recover in part here by picking on a different function instead. So I'm going to completely wave my hands at that little mistake. We'll fix that at some point. Why don't we just say fscanf won't be on the quiz? Fix it that way. So stir copy though. Stir copy is this function that's actually used useful, whether you used it, say, back for Caesar or Vigenère or something more recent, or nothing at all. But strcpy, as the name kind of implies, does the following. So strcpy in this man page says that it takes 2 pointers, to a destination string and to a source string. And what its purpose in life is to copy from source to destination. But implicit in this signature is what? Danger. What does strcpy not do? Which was the point I was trying to make a moment ago. Yeah. Exactly. It doesn't make sure that the destination, one, even exists. What if you pass in null? Doesn't seem to if we read the documentation check for that. But moreover, if you pass in a source string that is, for instance, a really long word, but you passed in a destination string, a buffer of chars that's only 3 characters long, the long one is not going to fit into the smaller one, and so you're going to get this overlap here, which we've seen thus far tends to cause what? So seg faults, because you're overstepping your bounds. Fortunately, strncopy, the n meaning it also takes into consideration length, takes a third argument, which is apparently of some weird type called size_t. But this is one of those type defs that I mentioned the other day on Monday. It's just an alias, a synonym for int. But it's a generalized way of calling it an int. So fortunately, even though strcopy and a related function, strcat, for concatenation of 2 strings, are dangerous for this very same reason as scanf, they're at least exist for those functions safer versions. And so the takeaway these days is there is very little, if any reason ever to use those functions. You might as well use these functions instead, unless you really don't need those checks to be performed. It turns out that printf and even fprintf, they too have their vulnerabilities. There are actually some sophisticated things you can do with the format strings that you pass to printf even, which isn't even about getting user input generally, but printing output out. But they too have these potentials for this thing called a buffer overflow. So who cares? Right? So it's one thing to sort of talk about and sort of wax over how you can write not only good code but bad code, but who cares? Well, to motivate this, much of the software still running on servers today, even your own desktops, was written in a language like C or C++ that generally do not check the boundaries of arrays, do not check the length of buffers. They leave it entirely to the programmer, the developer, to do. That's not a good thing when it's clearly so easy to make mistakes. And if you're writing not a few dozen lines of code like we tend to in lecture, but hundreds, thousands, millions of lines of code in something like an operating system, you're bound to screw up, right? So people make mistakes. This is why it's dangerous. So this is a snippet from the logs of one of my Linux servers under my desk. And I have this software that runs every night that analyzes the log files. So these big text files that just say who tried to get into my box from what IP address, what address on the internet, and how many times. And just in one night, for instance, someone from this IP address here, 64.whatever, tried to log into my personal server 476 times. Thankfully, unsuccessfully. 29 times from someone who was a little less determined, and then from someone in Italy 12 times from that particular IP address. Those failed logins refer to people that were actually guessing valid usernames, whether it was Malin as the username or root, which is the default administrator account name. They were just getting the password wrong. Now, people who were just guessing not only passwords but usernames were failing 1,688 times, 5,000 times. Again, this guy from Italy, 168 times. Wherever this thing is, 44 times. And this isn't even all that much. So odds are many of these people, if not all of them, are not some determined adversaries pissed off at David trying to get into his server, but they're these script kiddies, right? So this is one of these internet terms describing people who don't really have the skills to write software that actually compromise machines, but they're really good at Googling and downloading software that other people have written. And it's not all that hard to write a program that just tries some random IP addresses, some random computers on the internet, and bangs on them. In fact, some of you, for the hacker edition of Problem Set 2, though presumably you used your skills only for good, could have plugged in that same code to a program that not only tries to crack passwords, but makes an internet connection and tries to authenticate with a username against some server. So if you have in just one night a few thousand threats like these, and this is my little old computer in the computer science building under my desk. This isn't even a web server that the world knows about per se. So you can imagine Google and CNN, Amazon, any well-known server gets hit so many more times than this in a typical day. Well, there are people trying to get in, whether intentionally or simply by way of automation, these script kiddies. So let's go ahead and take a 2-minute break, and then we'll show you how they might actually get in. All right, we are back. Warm-up exercise. What does this program do? What does this program do? Yes? Good. So it takes 0 or more command line arguments, and then if 1 or more are actually provided, this loop actually causes each of the ith argv elements to get printed just as a string with a space separating them. So this is arguably pretty safe code. You're not even asking, you're asking the user for input, but only by way of the command line. But you're using this built-in mechanism of argv that you get sort of for free by writing a C program to actually store those strings in memory. So you yourself don't have to worry about getting those strings into memory. But now let's imagine using the same approach, trying to get command line arguments from the user for a program that quite reasonably is going to be larger than this. And because you've been taught to use hierarchical decomposition, and because it makes sense to have multiple functions, you decided to sort of factor out some of this printing mechanism into a different version of this program. So this is perhaps an unsafe version we'll see. Main now looks like this. It's almost the same, but instead of actually printing out the ith argv element itself, it's instead doing what with argv_i? So it's passing it to a function called echoarg. All right. Well, what does echoarg do? Well, echoarg signature is up here. It only has side effects because it doesn't appear to return anything. It's called echoarg. Notice that it takes as its only parameter a character buffer, a character array called s. We declare it const though. Why? Or why is that useful? Yeah, so it can't be changed. Now, granted, I'm writing this code, so if I don't want to change the buffer, maybe I should just not write code that changes the buffer. But again, this is all about sort of best practices, especially as you start to write code that other people use. By putting const there, can you make it much harder for them to actually misuse your code? Or they can it also allows them to trust, rather, that your code is not going to do something like change the values they're passing in. All right, so now the only 3 lines of code that this function has is it apparently declares a buffer, a character buffer of some size. So we're going to assume that max buff size is some constant that's sharp defined elsewhere in the file. So maybe it's 10, maybe it's 16, maybe it's 4, whatever. It's some constant. Now we're using what we claimed was this unsafe strcpy function. So strcpy is apparently going to take what is in S and put it into buff, this 4-byte or whatever character buffer. And then which of those is it going to print? So it's just going to print buff. All right. So it's not a useful program per se, but if you can kind of extrapolate mentally that, you know, if you slap some more lines of code here and here, this might actually be a compelling factorization of code, because maybe this function in reality would be doing more interesting stuff than this. All right. So the problem with this, though, is what? To tie together the stuff before break. Why is this unsafe? Yeah. So it's only allocating max buff size, but is there any code in there that's preventing me from typing in supercalifragilisticexpialidocious? That was really hard to say. Is there anything? I mean, there's nothing preventing me from typing the longest of strings to going to, again, some work of Shakespeare, copying it onto my clipboard and pasting it into this program, thereby most likely exceeding whatever the hard-coded size of this buffer is. Because strcpy, again, makes no checks as to how long this string actually is. So let's take a look. So among the source code that I have added to the course's website is this very simple program, echo.c. And this program very simply does that. So echo, I'm going to run foo. All right, that appears to work. So if I write now foo, 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 not so good. So take a guess as to what the buffer size maybe is for this actual program if we look at all the code. It's 3. It's 4 maybe, right? So FOO and then a \0. But even that, maybe we got lucky. Maybe it's a size 1 and we just got lucky by touching memory that the operating system didn't notice we were touching. Well, if we scroll down here, it looks like, yeah, define max buff size is actually initialized to 4. Well, let's see why this is so dangerous. It's not all that useful to just write a program that a user can crash, right? It kind of sucks if they run it and it crashes, but it wouldn't seem at first glance to put you at risk. Well, what if instead, though, the program you're writing isn't some silly little command line program that just user Malin gets to play because it's like Game of 15 or Sudoku, but rather you're writing a web server. So you're writing C code that gets compiled, put on a web server that is actually serving up web pages. As in fact, fairly high-performing web servers are absolutely written in languages like C and C++. And it's the programs you run on them, like PHP code, that are executed by programs, web servers written in lower level languages like C or C++. Well, suppose that this program had one other function in it. So this is courtesy actually of Mike Smith, I should say, current Dean of FAS. In addition to serving as Dean, he also knows how to crack into computer systems. And he provided us with this code. So this is the same program, but with the addition of one function up top. And this function is called gotcha. Doesn't seem to do all that much of interest except print out gotcha. But what's really interesting about this very short program, but very dangerous program, is that a determined adversary, a bad guy, if he bangs on this program enough, whether it's run at the command line or worse, at a web server where other people on the internet can access it, we can actually induce the function called gotcha to get run even though there's no invocation of gotcha in this code. To be clear, is there any line of code that should cause gotcha to be run in this program if I compiled it? I mean, the only mention of gotcha is in the definition of this function at the very top of the file. I don't have any other mentions of gotcha. So it sort of just seems obvious that gotcha might exist, but I'm not actually calling it because there's no function call. Well, let's take a look now. So this code is in the same file here, echo.c. I have just an additional line of code, an exit line, just so that we can actually see the result before bad stuff happens. But this is the same program. So the goal is to be able to type a bunch of command line arguments. Echo arg gets called. Those arguments should get printed, but then nothing else should happen. Gotcha is not actually invoked. Well, the interesting thing is that, as we said a couple weeks ago now, when you lay out your computer's memory, there's a whole bunch of stuff that actually goes in here that you yourself don't have direct control over. So you do have the stack, and on the stack goes things like the arguments to main, and then main's own local variables. And on top of main goes something like foo, or in this case, echo arg's local variables, and any arguments passed into it. And if echo arg itself calls some function bar, well, bar is going to get its own stack frame, and you're going to get all these stack frames that are memory, chunks of memory dedicated to each of those functions. But what we haven't focused on just yet, and you would focus on in a course like CS51, which is systems programming, lower level programming, it turns out that the operating system too, the runtime environment that's running your programs actually uses the stack as well. Because we've kind of been taking it for granted that when a function is done executing, you reach that closing curly brace, well, that's it. The thing gets ripped off the stack, the frame goes away, and the program sort of reverts back to using the previous stack frame. And when that function is done, then it goes back to the earlier stack frame. But there has to be some mechanism for actually remembering how big all of these stack frames are, right? Some function might have a huge number of local variables or a really big array. And so these frames, even though we tend to draw them as equal-sized rectangles, they could be really different in size depending on what the function's doing. So somehow you have to keep track of where each of those frames is, and specifically where the program should return to when some function's done executing. So we haven't focused on it all that much, but at the very top of your program's memory space are the zeros and ones that represent the compiled code. So when you compile a program into zeros and ones that get executed, much like the variables you're using have to somewhere be in RAM, well, if you're going to run that program, the program itself has to be slurped off the hard drive, loaded into RAM, so that the bits comprising the program can be fed one by one or 8 at a time, whatever, into the CPU. So this text segment, so to speak, which lives above the heap and above these things. Initialized data and uninitialized data means global variables that you give values to statically at the time of writing the program versus dynamically. Those things come above the heap and well above the stack. But what happens then in the stack is inside of or next to these stack frames are not only the arguments passed to a function and the local variables for a function, but also the address of the function that called the function to which this stack frame belongs. In other words, unbeknownst to you, or at least up until now, what the computer is doing for you is it's remembering what function should get called after this one's done by tucking away a 32-bit address on the stack, so that it knows by default when it tears off a stack frame, it should look in a specific 32 bits and say, oh ha, I was executing in foo at address 1, 2, 3, 4, 5, 6, 7. Let me now go there. So there are these return addresses that are saved on the stack. But the problem now is that you, the programmer, have the ability to yourself put things on the stack. But you have to specifically say, to be safe, how many bytes you want to use. So suppose that you only allocate 4 bytes on the stack, but you try to put 8 bytes there, or 20 bytes there, a huge word like the Mary Poppins word, right? Where is that going to end up? It is going to end up in memory, but if you've only reserved 4 bytes and you try to write a bunch more, you're going to be overwriting someone else's data. And based on this story, what data might you potentially be overwriting? The return address. In other words, if you are smart enough or lucky enough, you can clobber those 32 bits that were tucked away on the stack, not by you, but automatically when this function was called, that tell the computer what address to jump to start executing the next function. So if you're lucky enough to figure out where those bits are and to plop down a new 32 bits that refer to the address of some other function, you can effectively force your program to veer off on a detour and execute some function at some completely different address that the original programmer did not intend. So years ago, or maybe even today, if you've ever downloaded off the internet some kind of crack utility so that you can get rid of some serial number requirement for some program or any kind of registration requirement, well, programs are laid out in memory, those kinds of things just like this. And if you have a function called check serial number or check registration key, any kind of code that the owners of that software embedded in there for the purpose of checking whether or not the user actually has a legitimate copy, well, again, if you're sort of malicious enough and illegal enough and smart enough or lucky enough to figure out what those addresses are in memory, you can effectively trick the computer into skipping over addresses and jumping to other functions altogether, like the function called start program for free. Right? So it's the same idea even if you're trying to crack into static binaries that are stored on your hard drive. So let's see what we can do here. It's hard to simulate this at the command line because I can pretty much only type some basic punctuation, alphabetical characters, and numbers. But if you actually have access to the full range of ASCII characters, you can be a little more clever. So what I have here is a little Perl script. Perl is a scripting language that doesn't need to be compiled per se. This program does not do all that much. Almost every line here is a comment. But what we did, rather by trial and error, is figure out this. We declare a variable, which in Perl are preceded by $signs, has some number 1, 2, 3, 4. This is intentional though, followed by some weird looking stuff. So some hexadecimal characters that were only figured out actually by a former student, Jason Gao, last year by trial and error, just by playing around, banging on the computer, figuring out how things are laid out in memory. So the purpose of this argument is, one, to save me the trouble of trying to type something that's fairly cryptic and certainly hard to remember. So this script, this Perl script, just going to automate the hacking process for me. These 4 bytes up here, 1, 2, 3, 4, their purpose in life is going to be to fill that buffer, the buff size of 4, so that the rest of that stuff ends up where? After those 4 bytes. So somewhere unsafe in memory that normally would cause a seg fault, and maybe it still will. But if I'm lucky, and if Jason was good enough, these 8 bytes here might very well perfectly overlap, among other things, that return address. And in fact, guess what these 4 bytes actually represent? Hello world? Not hello world. Oh no, okay, but that would be consistent with things we do in this class. But let's take a look. So I'm going to actually run GDB on this echo program just to show you how you can actually figure this out besides trial and by error. So I've just run the echo program, which had 3 functions, gotcha, echo arg, and main. I'm going to go ahead and just print out gotcha. So just like you can print out variables and the addresses thereof, you can also print out the addresses of functions. Because where do functions live in this big picture of memory? in the text segment. So if you with GDB print out the name of a function, you see where it is in memory, aka in the text segment. And this long-looking hexadecimal string is what? 0x8048794. Well, I'm not going to remember all of those digits, but let's go back to this program and open up hack.pl. The last few were, let's see, 8794. Well, let's take a look. Ooh, interesting. 8794. Now, there seem to be in the wrong order, but that's intentional. And problem set 5, as promised on Monday, will sort of explain why sometimes bits are sort of arranged in the wrong order. This is called little endian order as opposed to big endian order. But that's actually the same pattern of bits, the same hexadecimal number, just kind of reversed. But that's intentional. So let's see what happens now. If I run echo with the word foo, I seem to be safe. If I run foo, 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 bad, okay, because I'm clobbering some stuff. And it sounds like I'm clobbering something important. Maybe I'm clobbering the return address of this function with something like OFOO, which happen to be 4 bytes, 32 bits that maybe just are perfectly overlapping that address. But I can actually run hack.pl, which is just, again, this little script on the echo program. And what this is going to do is run the echo program with that hard-coded set of arguments that Jason figured out. And wow, what just happened? So gotcha got invoked, because what does gotcha do? Gotcha prints out gotcha, exclamation point. I simply, even though this looks a little weird, all this is doing is running echo with this funky looking string of arguments, which Jason figured out by trial and error. So we've just run, again, hack.pl's feeding those arguments to echo. Now there's some garbage here, because some bad stuff happens, but the point is we have just executed code that the original author did not intend. And how would we go about figuring this out? Well, the way that many adversaries would figure out that a program is buggy and has these vulnerabilities is brute force. You hit the hell out of the server just by hitting it with the word foo, and then hit it with foo foo, then hit it with foo foo foo. In the context of a web server, this is like filling out a web form again and again and again with a whole bunch of bogus data quickly as possible and seeing if you actually cause that web server to crash. Because if a web server is written in something like C, and you can cause it to crash by way of a seg fault, what does that probably suggest about the program that is the web server? I mean, there's a bug. Like, it doesn't necessarily mean you can hack into it yet, but there's clearly a bug if you, just by providing some bogus and maybe really big input, you can cause someone's web server to crash. So if you can cause it to crash, well, you might have just kind of screwed yourself for the night, because now you have to wait for the owner to bring it back alive or reboot the server, right? So again, this is not sort of, don't try this at home, because these are not good lessons perhaps, but there's interesting takeaways here. So once the server's back alive, you now know that your target has some kind of bug. And any time a computer program has a bug, it's a potential opportunity for an adversary to do something bad. And we've just seen with the simplest of programs that an adversary can induce unintended code to get executed by, one, banging on the code like Jason did last year, figuring out what the addresses were in memory, and finally, when you hit the right address, when you pass in the right randomly generated string or carefully crafted string, can you cause the program to do something that wasn't intended. And very often what happens is that most people don't have a function called gotcha embedded in their web servers, but rather some function related to administrator privileges. So what generally happens is if you can induce unintended code to get executed, you can very often induce functions to get executed that give you, the bad guy, administrator access to the machine. Or maybe that function on Amazon.com is something like credit me $100 or something silly to that effect. You're inducing code to get called that might have any effect, but that's unanticipated because the authors didn't think anyone else but they could cause it to get invoked. So any questions on these things called buffer overflows or these exploits? Yeah? Good question. So why is the address the same every time you run it? It's partly because we carefully planned ahead. And the way we compiled this program was with a very specific set of flags that deterministically lay things out in memory the same again and again. So absolutely, with more complicated programs, it's quite possible that things won't get laid out in memory the same way. In fact, there are compilers now that if you turn on certain flags, special hyphen whatever flags, you can actually proactively tell the compiler that when you compile this program, make sure that you're sort of moving things around in a somewhat random way, so it's not so deterministic. And in fact, there's also this this trick, there are special libraries you can compile into your code that insert what are called canaries into your code. And a canary, so back in the day when folks used to spend a lot of time in coal mines, I mean, one of the tricks supposedly was to bring down, sadly, like a bird. And if the bird suffocated, it meant it was time for the humans to get out of the cave. And he used it as sort of a sign that something bad had happened, but you might still have time to recover. In the context of computer programs, you can compile in libraries. Things called stack guard is one of them. And what this does is it inserts sort of a random number on the stack in a location that's not being used by anything else. And what the program does, because it's using this library, is it constantly monitors that canary value, that really big integer. And if it detects that, whoa, this integer changed and it shouldn't have, it will then terminate the program so as to protect against adversaries that might be mucking around with the memory space. But in our case, because we're not using such libraries, because we're compiling with these specific flags, because we're running it on the same computer, nice.fas, again and again, these addresses are in fact deterministic. That is, they stay the same. Another question in front? No? OK, so we're going to introduce one more trick that will be not only related to something we saw earlier with like fscanf and fprintf, those file pointers, but will also be useful with problem set 5. So let's take a look at structs1 structs.h. So struct, recall, from problem set 4 if you've dived in, allows you to clump some related variables together in a new data type, a data type that itself has multiple primitives, multiple smaller variables inside of it. You can simultaneously use, when defining a struct, that trick called typedef, which allows you to give your struct a name. By that I mean this. Normally if you implement a struct, and say something like struct foo, and my foo object is going to have an int called x and an int called y. Well, normally you would, if you want to then declare a struct foo in main, so if you have int main, int argc, char star, argv, if you have main and you want to declare a variable of type foo, you actually have to do this nuisance, struct foo f. And that gives you a variable called f that's of type struct foo. Just gets tedious typing struct all the time. So what typedef allows you to do is to simultaneously declare the struct, but give it a name that will allow you to declare it later with just give me a student called s instead of a struct student s. So it's really just an aesthetic thing. It's certainly convenient. So we decided for this example we want a structure that represents the notion of a student. And a student arbitrarily is going to have an ID number, which is just a big int, a string for a name, and a string for their house. And this data type is again going to be called a student. Well, let's see what we can do with this. In structs1.c, notice I'm including CS50's library, some of the standard libraries, the string library, and then our own header file, since I want to use this header file elsewhere. Arbitrarily, I've decided that there will be 3 students in this class, so that the demo does not go on forever. And all we're doing now is the following. Notice that this first line is declaring class. Now this isn't class in the Java object-oriented sense. I'm declaring a classroom full of students. So students, the constant is 3. So in English, what is this actually declaring for me? Or in C terminology? Yeah, an array of students. So now I have a whole chunk of memory, each of whose cells can fit not just a student's ID, but a student's ID and their name and their house all together, which is why now we're already able to build up more interesting data structures. And we're going to do the following. I'm going to have a for loop here that iterates apparently 3 times from 0 up to this constant students. And on each iteration, it's going to ask me for the student's ID, and it's going to use getInt. But how is it going to get the int into the struct? Well, this is very familiar syntax now, right? To get at the ith element in an array called class, it's class square brackets I. To get at the inner members of a struct, we introduce this new piece of syntax, the dot operator. This says dive into the struct and grab the data member called ID. Similarly here, does this say class bracket I dot name, store in the name field of this struct called a student some string that the user has provided, and same thing for the house. And then finally, the very last thing we do is, again, something related to Mather, and then later we apparently free these objects. So let's take a look. So make structs1. All right, now I'm going to run structs1. It's going to ask me for an ID. So this is going to be student number 1. Student's going to be John, and he's going to be in Cabot. Student ID 2. In Cabot. This will be Jane, and she will be in Foho. All right, student ID 3 will be David. He'll be in Mather. Ah, all right, so that's cute. How did this work? Well, one, we went and looped over all 3 elements of the array and just populated the ith student struct with an ID, with a name, and with a house, and then we just printed out a blank line for aesthetic reasons. Now, apparently, I decided it would be compelling to iterate again over that array from 0 up to the value of students, in this case 3, use that string compare function we've used before, strcomp, checking if the ith class member, the ith student, dot house equals Mather, quote unquote, and we do this by way of checking for a return value of 0, go ahead and just arbitrarily print out that that person is in Mather. But then the very last thing we need to do down here is, we're finally calling free to be consistent with best practices. Why are we calling free? Not for the ID number of each student, but for name and house. Get string, right, recall from Monday, actually calls malloc, maybe realloc, and is allocating memory. So finally, for the first time ever, are we actually cleaning up our own mess in memory and giving back to the operating system the memory we dynamically asked for by way of those calls to getString, or in turn, malloc. So a much better improvement. Unfortunately, the moment you hit this curly brace here, you've just wasted a whole lot of time because you've just typed in all this input, right? So you've checked that, yes, David's in Mather, but who really cares because we've just forgotten, sorry, about John and Jane and Cabot and Foho. So slightly more interesting is this new variant. So structs2 includes, for the first time, the ability to persist your data. That is, keep it around on a hard disk, which is quite compelling, certainly, for any program you might use on your own computer. So the first chunk of code here is identical. Declare an array of students called class, get some information about them, print out again who's in Mather. But now we have some interesting code. And it's not all that much to do something useful. Let's save these students to disk. So they're in RAM at the moment. In this array, let's dump them to disk and see what happens. So it turns out that there's this special pointer, this special data type called file, which because they decided to do this, it's all caps, file, and it's a pointer type. So file pointer. FP is just a convention. You can call it whatever you want. It means file pointer. In this case, it's a variable. It's being assigned the return value of some new function called fopen. File open that takes 2 arguments. The first is the name of the file you want to open, and the second is a string signifying what mode you want to open the file in. Take a guess what W means. Write. So if you wanted only to read it in and suck the memory into RAM, the bits into RAM, it would be R instead. And there's a couple other modes like append as well, if you want to just keep adding students to the file without clobbering existing ones. Just to be safe, we do check for null. Why do you think fopen might ever return null? Student just outright, the file called database just isn't there. There's nothing to write to. There's a problem. You don't have write access to the directory because you're in a directory that someone else has owned. Whole bunch of problems can happen. Checking for null is the way to ensure that you're not going to assume you are able to write there. Well, let's see what we do next. We have this loop here that iterates over students. Not all that interesting. Now we're using fprintf. And finally, does fprintf make a little more sense? Rather than printing to standard out, stdout, or even standard error, stderr, from Monday, now we're printing to a file pointer that we ourselves opened. Whereas standard out, standard error, standard input, you get for free. They're automatically provided to you when you run a program. What do I want to print to this file? An int followed by a \n, swapping in that ID value of the ith student. Then print out a string followed by a new line. Then another string followed by a new line. What should those strings be? Well, the student's name and the student's house. Once you're all done iterating over all the students, let's close the file with fclose, passing in the file pointer. We don't need the RAM anymore, so let's go ahead and just free what was in RAM. So if I run make structs2, what I'll now see is the following. So structs2, oh, notice in my directory there's a core file, which means I screwed up earlier, but there's no database. So let's see what happens. So structs2, student's ID 1, this will be John. In Cabot 2, this will be Jane. In Foho 3, this will be David. In Mather, we're going to get that stupid message. And then nothing happens but, ooh, interesting. Let's do an ls-l. Looks like database is 41 bytes, brand new, 2:22 p.m. So let's take a look at database. And there's how I decided to store this file. So it's not a very sophisticated file. In fact, you look at this and it's not quite clear what's what because there's no metadata. There's no sort of hints as to what's an ID, what's a name. I've just assumed that the first line is an ID, second is a name, third is a house, repeat, repeat, repeat. But recall, this is precisely what we did with problem set 4. So when we revealed to you the other day that these binary files in pset4, leet.bin and noob.bin, if I open them up with VI, bad stuff happens because they're binary. But if I instead use that program called xxd and do it in -b mode, -binary, and then look at noob.bin, what I actually see are zeros and ones. And the zeros and ones represent ints, which are a series of 81 ints, followed by 81 ints, followed by 81 ints, because we decided, based on how we wanted to write the code, it's just really easy to store 1,000 Sudoku boards by just stacking them one after the other after the other. And yes, it's not clear by looking at the bits what's what, but if you wrote the program that outputs those bits, you can certainly write the program that inputs those bits, reads them back in, so you have a file format. So now anytime you've saved a Word document, a .doc, or nowadays .docx, or a XLS file for Excel, or any of these known file types, there's just been some people at Microsoft or elsewhere that decided, you know what, we're going to create a file type that ends in .doc, and here is the pattern that any file saved in this format should follow. We, for this course, decided that the .bin format is going to have 81 ints back to back, again and again. That is the file format. I just decided for this silly program that the format of a database file is going to contain ID, name, house, ID, name, house. That is all there is to a file format, is a bunch of people got in a room and decided what the convention would be. Now, why is this useful looking ahead to problem set 5? So problem set 5, we're going to give you some files. We're going to give you files that you need to read into memory and analyze to figure out a murder mystery. We're going to hand you an image, a forensic image that I will make of the compact flash card on which, and one of so if you actually happen to stroll around campus on Monday afternoon, roughly after lecture, you can pretty much follow me and a photography friend from MIT as to where we went on campus taking these photos. If you were not so fortunate as to stalk us that day, you will receive soon a forensic image of the compact flash card, the memory stick that was in my friend's camera that has a whole bunch of photographs that we took. Unfortunately, I'm going to accidentally format that card in his camera before we make that image. So you're going to get a whole bunch of zeros and ones in a file that represents a memory stick, but we've erased, by formatting it, all of the useful information like what the layout is of that file. But fortunately, much like Word documents and databases and bin files have a format to them, so do JPEGs, which is the format that photos are typically stored in. Every JPEG in the world starts with a certain pattern of bits. And by knowing that, a forensic investigator can actually analyze a sequence of bits looking for that pattern, and odds are, though not guaranteed, odds are anytime they see that pattern of bits, you can assume, aha, here is the start of a JPEG. Let me start reading in these bits. I'm going to assume they're all part of a JPEG until I see what? That same pattern again. Now again, you're playing some odds here, because maybe by chance the picture of the leaf we took happens to have that same pattern of bits, just in a different context. So it's not a perfect science, but it's going to be an art, a skill that you apply for the resurrection of those photos and the murder mystery for problem set 5. But otherwise, we'll see you on Monday for lecture and Wednesday for quiz.